Okay, thank you very much for attending my lecture. I am very happy to be with you. And today I will talk about the JSON-B performance. The slides is available already. This is a joint talk with my colleague Nikita Glukhov. This is a picture of the elephant with all projects I was working on. Maybe you know some of them. I am a research scientist at Moscow University and also work in the Postgres professional company. And most interesting to me now is, most relevant is that I am major Postgres contributor. And my colleague, Nikita Glukhov, he's working also in Postgres professional company. He is also Postgres contributor, and for several years he did several big projects already. So we today will talk about the JSON performance, and the reason why I decided to talk about this here, because we know that JSON is, as I said, that one type fits all. You know that modern architecture is a microservice architecture, and JSON is very good and very good for the for this architecture, because client applications, front-end, back-end, and now database, they use JSON. It is very easy for startup to start their project. You don't need bother about the relational, scheme, how to make it proper, how to make it. It's very difficult when you start your project, when you start your business, to predict what the schema will be in the several months. With JSON, you don't have any problem. Just have JSON. And all server-side languages support JSON. SQL standard support has a SQL JSON officially, so it's not like something different from SQL. And what's very important, that JSON relaxed object relational mismatch, because in your code you work with the objects. In relational database you work with relations, and it always you have some contradictions between the programmers and between DBA. But when you use JSON, there is no actually any contradiction. So that's why JSON becomes very popular. And I would say that now I see that JSON-B rush, because I'm speaker at many conferences, and I see that many people, they asked me about JSON, and they said that we don't know much about SQL. We use JSON, and what we need is just to have JavaScript instead of SQL. And that is a very interesting idea, actually. I have some thinking about this, because actually it's easy. I can internally transform JavaScript to SQL and execute it. But that's about my future project. And JSON-B is actually the main driver of Postgres popularity. People say that, you see the create table JSON. It's a common mistake. They put everything into JSON-B. That is because people don't know about how JSON-B performance. I will talk about this later. And another reason about this talk that nobody made the comparison between performance of JSON-B operators. So this talk I will explain which operator to use, which operator, what is better, and so on. And another reason is that I work at 25 years in Postgres, maybe 26. I started from 1995, and almost all my projects, they connected to the extending Postgres to support this non-structural data. So we started from arrays, HStore, full text search, and JSON-B, and now working on the SQL JSON. So this is my interest. And I believe that JSON is very useful and for Postgres community. You see this picture. This how popularity of 4 databases changed over time. the only database which grows is the Postgres. I use the official, official numbers from the DB engine, and it's relational popularity. And you see that Postgres becomes very popular from the time when we committed JSON-B into Postgres. So that's why I think, at least I believe, that JSON-B is one of the main driver of popularity. And because NoSQL people, we attract another category of people, another kind of people. People who first time started working with Mongo, then becomes upset and go to Postgres, because Postgres got a good JSON data type. And our work on JSON-B made possible SQL standard 2016. So the success of Postgres made this. All other databases now have JSON. And that's why we have SQL standard on this. So to me, it's very important to have to continue work on JSON in Postgres, because we have many users. These are numbers from JSON from PostgreSQL popularity survey made by TimescaleDB, I remember. And you see that the most popular is JSON-B. It's the biggest popularity. If we take the popularity in Telegram chart on PostgreSQL, it's a Russian. We have several thousand people there. It's very active. Anytime you have several thousand people online. And JSON and JSON-B is the third popular word used by Postgres people. So the first is select, the second is SQL, and third is JSON-B. So this is like some argument that JSON is very popular in Postgres community. So we were working on several big projects. Some of them already committed, some of them waiting for commits. Yes, and but now we change the priority of our development. So we want to have JSON-B, the first-class citizen in Postgres. And so it means that it should, we want to have efficient storage, select, update, good API. The reason for this is that SQL JSON is important, of course, because this is a part of standard. But actually, people who work with Postgres, they have no idea to be compatible with Oracle or Microsoft. I know that people, that startups started with Postgres and never changed it. And JSON-B is already a mature data type. We have a lot of functionality in Postgres. So, and also we have not enough resources in community to even to review and commit the patches. You see that 4 years we have patches for SQL JSON functions. A JSON table will wait also 4 years. So maybe for PG15 we maybe have some patches committed, but I understand that community just has no resources, and my interest mostly is concentrate on improving JSON-B, not the standard. So I'm mostly aware about Postgres users. And I'm not very interested in the compatibility to Oracle or Microsoft SQL Server. So this is a popular mistake. People put everything into JSON, and that's not a good idea. You can see very easy that ID outside of JSON-B and ID inside. If JSON-B is growing, the performance is degrade very quickly. So this, don't do this. And now we want to demonstrate the performance of nested containers. No, we created sample tables with nested objects, and we test several operators. It's an arrow operator. You know, most people use arrow operator to access the key. Extract path operator is a hash arrow. The new one is subscripting. So you can have like an array syntax. And another one, the fourth, is a JSON path. So what is your, do you know which is better? Nobody knows, actually, and me too. So we did a lot of experiments, and now I will show you some graphics. On this is a raw JSON-B size, and ordinate is a execution time. This is an arrow operator. JSON-B grow, and execution times grow. So the reason for this I will explain later. The same behavior actually is for other operator, but it's a bit different. Interesting that subscripting behave very good. And we have the color. It's a nesting level. So we measure execution time for the different nesting level. This 2 kilobytes means that after 2 kilobytes we have a toast. JSON-B becomes toasted. That's why we have we have degradation of performance. But before we have the constant, and we see that overhead for nesting. So the deeper we go, the performance is more worse. And here is a slowdown relative to the root level. So the picture is also very strange. Relative to the root level for the same operator. So this extract path operator, JSON path, and subscripting. Arrow operator again shows some instability, is not very predictable behavior. If you see the slowdown relative to the extract path operator, situation becomes a bit better, but a bit clear, because we see that JSON path is the slowest. JSON path is the slowest, and subscripting is the fastest. It was very, very unexpected behavior, but you know now this. After 2 kilobytes, everything becomes more or less okay, because detoast dominates. So you have to, overhead of detoast becomes more major contribution to the performance. This picture demonstrates the best operator depending on size and nesting level. So it's the same data, but in different picture, different format. We see that arrow operator is good only for small JSON-B and root level. I would say for root level, you can safely use arrow operator. For the first level, I would not use for the big JSON-B. Subscripting is the most useful, good. And JSON path is a bit slower, but you see that here, you see some JSON path. But value of JSON path is not about performance, because JSON path is very flexible. For the very complex queries, you need JSON path. But for the simple queries like this, just access key, overhead of JSON path is too big. So all operators, they have a common overhead. It's a detoast and iteration time, But arrow operator, very fast for the small and root level, because it has minimal initialization. But it needs to copy intermediate results to some temporary datums. Let's see this picture, how arrow operator executes. So you have toasted, detoast. This is a toast pointer. You detoast, and then you find key 1. you find some value, and you need to copy all this nested JSON-B containers to some intermediate datum, which go to the second execution. So key 2, and then you copy string to result. This is example just for root and the first level. But you can imagine if you have 9 levels, more levels, you have to repeat this operation. You have to copy all nested container to memory, to some intermediate datum. This is a price for the abstraction. In Postgres, you can combine operator. So that's why this arrow operator works like this. But extract path works different. Actually, not extract path, but subscription JSON path. They have they share the same schema. Again, you have toast pointer, you detoast, and then you just copy string to result. You find everything in one inside, and there is no copy overhead. So the conclusion is that you can use safely arrow operator for root level of any size, and for first level for small JSON-B. Then use subscripting and extract path for large JSON-B, and if you have higher nesting level. This is my recommendation. JSON path is slowest, but it's very useful for complex queries. Now we want to analyze the performance of another very important queries is contains. So you want to find some key value in JSON-B. So again, we have a table with arrays of various size from 1 to 1 million entries. So, and we try to find several operations. It's contained operator, contain. JSON path match operator. JSON path exist operator with filter. And SQL, 2 variants of SQL. One is exist, and another one it's an optimized version of this one. And we use this query like we look for the first element existed. Actually, it's a 0, and we look for the non-existent operators, which is -1. And we see how different queries execute. Well, we see that if we search first element, the behavior more or less the same, except 2. Contains operator is the fastest. Before toast, before JSON-B toasted, we have a constant and constant time. And also we have a match operator in lax mode. You know this, what is mean, strict mode and lax mode. JSON path has 2 modes, which you instruct interpreter of JSON path how to work with the errors, for example, inside and so on. In lax mode, execution stops when you find the result. And if since 0 is the first member in the array, it happens very fast. But in strict mode, the same. You see green. You have to check all elements, because in strict mode you have to see all errors, possible errors can happen. Fortunately, lax mode is default. So you see that for search first element, but for non-existent element, behavior the same, because you have to check all elements. You check all elements, you can't find -0, And the difference between performance is just of different overheads operator. So this is speed up relative to SQL exist. And conclusions is that contains is the fastest. SQL exist is the slowest. And the performance between match and exist operators for JSON pass depends on how many items you have to iterate. But the most interesting, you see on all pictures, you see that performance very dependent on how big is JSON. After the JSON not greater than 2 kilobytes, the compressed size, you see the performance very degrade. That's why we analyze the toast very detailed. And this part I call the course of toast. This is unpredictable performance of JSON-B. People actually ask me why, when we start the project, we have very good performance, but then we see sometimes that performance very unstable. And this query, this example demonstrates this unpredictable behavior. So very simple JSON with ID and some array. And first you have select very fast. So we see that buffers read 2,500 and some milliseconds. After you update, very simple update, you have 30,000 buffers and 66 milliseconds. So just it's this people asking me why it happens, but it happens because rows gets toasted. So toast is a very useful technology in Postgres which allows you to store very long objects. We have limitation that for 8 kilobyte page size, we have tuple limit to 2 kilobytes. Everything that's bigger than 2 kilobytes, we move to some another storage. And we have implicit join when we get value. But situation is much worse, I will show later. But here is the explanation. You can install a very useful extension page inspect and see that original JSON, which stored inline, so not toasted, just inline in heap, we have 2,500 pages and just 4 tuples per page. After update, we see very strange. We see strange that we have now 64 pages with 157 tuples per page. How it happens? Because long JSON replaced by just tuple toast pointer. So tuple becomes very small. But everything moved to the toast. And we can find, using this query, we can find the name of toast relation, very easy. And then we can inspect how about chunks where we store these long values in the toast. And access to the toast requires reading at least 3 additional buffers. 2 toast index buffers, because you access toast not directly, but using some B3 index. So you access 2 toast index buffers and 1 toast from heap buffer. So easy calculation, you explain that why we have 30,000 pages after update. We have 64 buffers and overhead. 3 buffers multiplied by number of rows, 10,000. So this explains the very bad performance of the small update. And if you know what is a toast, I can explain it's very detailed. So toast just compressed and then split it by 2 kilobytes chunks and stored in the normal heap relations. You just don't see. It's hidden from you. And to access these chunks, you have to use B-tree index. And you have overhead, just to read only few bytes from the first chunk. You have overhead 3, 4, or even 5 additional blocks. That's the problem of Toast. And Toast also very complicated algorithm. It uses 4 passes. So Postgres tried to compactify tuple to have it 2 kilobytes. We try to compress the longest fields. If it's not compressed, if the resulted tuple still more than 2 kilobytes, it replaces fields by Toast pointer, and value of fields move to the Toast relation. Actually, you see that's pass 1, pass 2, pass 3, pass 4. So it's not easy. The original tuple replaced by this. You see, this is a plain, some field which not touched. This is compressed field, and 4 tuple pointers, which pointed to the Toast storage. We have this here. And when you access, for example, this one, you have to read all this one. Even if you access plain attribute, plain, you don't touch all these Toast. But once once the attribute is toasted, you have to combine all these chunks. So first you need to find all chunks, combined to one big buffer, and then decompress. So this is a lot of overhead. Let's see this example. Example is very easy. We have 100 JSONB different sizes, and each JSONB looks like key 1, very long key 2 array, key 3, and long key 4. And we measure time of arrow operator. We repeat 1,000 times in query, then to have a more stable result. This result, you see? So we generate the query. We execute 1,000, and then resulted time divide by 1,000 to have more stable time. And we see that key access time linearly increase with the JSONB size, regardless of key position, of key size and position. And that's a very surprise for many people, because they say, I have just one small key. Why access time is so big? Because everything after the 100 kilobytes, everything in Toast. And to get this small key, you have to detoast all this JSONB and then decompress. You see that 3 areas. One is inline. The performance is good and time is constant. The second one is a compressed inline. When Postgres success to compress and put into inline. So 100 kilobytes, it's actually 2 kilobytes compressed, because here is a raw JSONB size. After compress, 100 kilobytes becomes 2 kilobytes. And you have some gross access time because you have to decompress. And after 100 kilobytes, everything toasted. It's not fit 2 kilobytes, even after compressing. And here is the number of blocks read. To 100 kilobytes, you see no additional block to read, because everything in line. After you read more blocks. Even you see that 30 blocks. It's too much. Yes.
Have you done a comparison with Mongo, and in what areas does Mongo suffer these same issues?
Yes, I will show the last slide. It will be about
Thank you.
some comparison with Mongo because all people interested how it's Mongo. Yes. And it's the same. Now you see that this is a compressed size. So you see that only 2 areas. Inline, this is size 2 kilobytes. After 2 kilobytes, what compressed inline, they are more clearly seen because the size is compressed, 2 kilobytes. And the problem is that access time doesn't depend on the case size position. Everything, suffers from the toast. Another problem is the partial update, because people also complain that I just want to update small key. Why the performance very bad? Again, because Postgres toast, because toast mechanism, algorithm works with JSONB as a black box. Because it was developed by Jan Wick when there was no, when all data types were atomic. Atomic. But now JSONB has a structure as other data type. And TOS should be more smart. But currently, TOS storage duplicated when you update, while traffic increased and performance becomes very slow. Also, you see that the example. We have 100 gigabytes heap and relation 78 megabyte. After update, we have TOS table doubled, and also we have 130 megabytes while traffic. After small update, because Postgres doesn't know anything about structure of JSONB. It's just black box, double size and lock this size. That's the problem. So we have our project started this year, in the beginning of this year, JSONB detoast improvement, and our goal, ideal goal. So we won't have no dependency on JSONB size and position. So our access time should be proportional to the nesting level, and update time should be proportional nesting level and key size, what we update. Not the whole JSONB size, but what we update only. Original toast doesn't use inline. Once you toast, we have a lot of space in heap, just free. So we want to use this inline as much as possible, because access to the inline many times faster than to the toast. And we want to compress long fields in toast chunks separately for independent access and update. So if you want to update something, you don't need to touch all chunks. You need to find some chunk, update it, and log. That's all. But this is ideal. And we have several experiments. So we have a partial decompression. We sort JSONB object key by length. So short keys, they're stored in the beginning. Partial detoast, partial decompression, inline toast, compressed fields, shared toast. So not much time, so I just say the names. But and in place updates. And here we see the result. This is the master. How master behave. After, for example, after partial decompression, after the partial decompression, some keys becomes faster. Here all keys behave the same. But after partial decompression, some keys becomes faster because they are in the beginning and decompressed faster. After the sorting case, we see another keys came down because key 3, for example, key 3, was blocked by long key 2, was blocked. After the sorting, key 3 becomes behind the long objects. And this is, you see, it becomes lower. And after all this experiment, we get very interesting results, very good result. So we have still growing time, but that we understand for the big arrays. And the first element in array we access faster than the last, of course. But what to do with this? We find it's another problem. But you see that some very simple optimization, we still stay with heap, with toast. We can find like several orders of magnitudes performance gain. Here is a very interesting stack picture, how many different optimization gain to the performance. So we see that this is a short keys, key 1, key 3. For example, here, key 3 gain sorting, because it was blocked by key 2, but after the sorting keys, it got a lot of performance gain, and so on. So it's easy to interpret this picture. Slides available, but not much time. And if we return back to these popular mistakes, the mistakes becomes not very serious, because now this ID, which stored inside JSONB, not growing infinitely, but stay constant. Still have some overhead, but it's okay, more or less, after all this experiment. We have also make some experimental slice detoast, so we improve access to array elements stored in chunks. And the last, you see these arrays elements, they now not growing infinitely, but stay some, you see there's some plateau. But this is very experimental. Update, 10 minutes, okay. Update is very painful process in Postgres, and for JSONB especially. Here is the master. After the shared toast means that we update only selected chunks. Other chunks we share between versions. That's why we say shared toast. After the shared toast, we have good results, and only last array elements still grow, because it's difficult, last element in array. But after in-place update, we have a good, I think that's a good, not good results for updates. Again, for updates, we have, again, several orders of magnitude. Updates is very important because people use JSONB in OLTP environment, you know. So updates is very important. Access is good for the OLAP, for analytical processing, but for OLTP, it's, updates is very important. This is the number of blocks read. You see clearly that we have much less blocks to read. Just to remind you that this is a not linear scale, this is a logarithmic scale. So it's this WAL traffic. In master, you have very big WAL traffic. In shared, it's a bit smaller. And here we have very controlled WAL traffic. You logged only what you update. The remain is people asking, what if I use JSONB and relational structure, which is better? So we made several, again, access the whole document testing. So this is JSONB, this relational tables. For relational, you need to have join. In JSON, you don't need join. and how it, we have several queries, and this is a resulted picture. So you see that this is a very, very fast. So the darker blue is the good. This is the bad. So to access the whole document in JSONB, it's no surprise, very fast. Because you don't need to, you just need to read it and go. For the, but when you want to transfer JSONB, you have problem because you need to convert JSONB to the text. Conversion to the text in Postgres is also painful. You're never surprised. You need to check all bytes, all bits, to quoting some bad characters and so on. So it's not easy operation, and we see that for the large JSONB, the time is not very good, and becomes also what here. Here we made experiment when we don't need to transfer in textual form as text. This is called UB-JSON. UB-JSON. We transfer to the client just binary transfer. And we see that situation becomes better. There is no degradation. For the relational, you see the problem. We transfer, this is a time for select, this is for select and transfer, and this is transfer in binary. There is a method, you can, for erase, you can transfer binary. And clearly we see that JSONB here is a winner. And that's explained why it's so popular. Because microservice, what is a microservice? It's a small service which expects some predefined query, some aggregate. And JSONB is actually aggregate. You don't need to join data from different tables. You just have aggregation. And microservice access this JSONB, and performance is very good. Very simple setup. So if you use a microservice architecture, you just happy with JSONB. That's popular. But when you access key and update, you have a bit different result. Because this one, the first one is an arrow operator, and the last one is relational select. Relational is a winner. This is a current situation, and this situation with JSONB after all our optimization. So you see that after all optimization, we as fast as relational access. You understand that for JSONB to get some key, you have to do some operation. But for relational, you just need to get you don't need any overheads. And very nice that after our optimization, we behave the same as relational. But currently, for current situation like this. So if you want to update, especially, update and access key, relational is winner. Our optimization helps a lot. This is like slow down. You see that JSONB slow down against this relational. But after our optimization, we have, you see it like the same, like relational. And the same as update slow down. So for update, we still have some. This is a JSONB original in master in PG14. And here is our. So our optimization helps for updates. And also wall traffic. So we have for master, we have a lot of wall traffic. We logged a lot. This is a relational. And this is our optimization. There looks like the same. Also, we have access array member, very popular operation. We have array, and you want to get some member of this array. Yeah, we have for first key, middle key, and the last key. And here is a relational, optimized, and non-optimized JSON-B. So we see that access array member is not very good for the JSON-B, but with our optimization again we approach to the relational and update any member. We also compare how to update array member, and here is a JSON-B. This is a JSON-B optimized, and this is relational. Now, of course, when you update array member in relational table, it's very easy. You just update one row. And for the JSON-B, you update the whole JSON-B. We can be very big. But our optimization helps a lot again. This is a wall. And conclusion is that JSON-B is good for full object access. So microservices. It's much faster than relational way. In relational way, you have to join, you have to aggregate, and very difficult to tune the process. With JSON-B, you have no problem. Also, JSON-B is very good for storing metadata, in short metadata in just separate JSON-B field. And currently, PG14 not optimized, as I shown you, that for update and access to array member. But we demonstrated all our optimization, which resulted in orders of magnitudes for selects and updates. And the question is how to integrate now all these our patches to the Postgres. And the first step is to make a data type aware toast, because currently toast is the common for all data type. But we suggest that toast should be extended. So data type knows better how to toast it. And that allows many other developers made a lot of performance improving. We have example when we improve streaming. You know, some people wanted to stream data into the Postgres. For example, movie. It's a crazy idea, but they stream there. Before, you may imagine how it behaves slowly, because it's logged every time. You add 1 byte, and you logged all 1 gigabyte. Add another 1 byte, you log another one. After our optimization, we have special extension. It works very fast. We logged only this 1 byte. That's all. Because we made a special for byte A, streaming byte A. Special toast. So first, we need to that community accept some data type. Sorry, stop. Just 2 slides. So we have to do. It's on physical level, we provide random access to keys and arrays. On physical level, this is easy. We already have slice detoast. I shown you. We need to add some compression. But most important to make it logical level. So we know how to, which toast chunk we need to work on logical level. And this number of patches, this not exist, still not exist. Yes, but this is all our patches and our roadmap, how to work with community to submit all this picture, all this our result. And it's references. And I invited you to join our development team. This is not the company project, Postgres Professional. This is an open source project, community project. So everybody invited to join us. This is what Simon asked about non-scientific comparison, Postgres with Mongo. I said not non-scientific because scientific benchmark is very, very complicated task. Very, very. But here is non-scientific. We compare sexcan, Postgres in memory, Mongo in memory. Mongo need double size of Postgres because Mongo keep uncompressed data in memory. And we see that this is a vanilla Postgres. Vanilla Postgres, this is a Mongo. Mongo is much faster than vanilla Postgres. After our optimization, we have performance better than Mongo. But if we turn on parallel support, because all this without any parallelism, to compare. But after the parallel support, we have very fast Postgres in compared to Mongo. Yeah, but as I said, this is a Mongo when memory is just 4 gigabytes. And Mongo is not very good when you don't have enough memory. So it's behave like the Postgres. Postgres is much better, works with the memory. So that means that we have our community have a good chance to attract Mongo users to the Postgres. Because Postgres is a very good, solid database, good community. We're all open source, independent, and we have JSON. Just need better performance and to be more friendly to the young people who started working with Postgres. This is a picture of my kids. They climb trees, and sometimes they tear their pants. And I have 2 options. I can forbid them to do this. I can teach them. So let's say that JSON is not the wrong technology. Let's make it a first-class citizen in Postgres. Be friendly. Because still some senior Postgres people still say that, oh, relational database, relations, you need just read these books. But young people, startups, they don't have time. They can't hire some very sophisticated senior database architecture, you know. They want to make their business. They need JSON. So my position is to make Postgres friendly to these people. This is actually our duty. Database should be smart. People should work, should do their business, their projects. So that's why I say that, and at least at the end, we are universal database. So I say that all you need is just Postgres. With JSON, we will have a lot of fun, a lot of new people, and our popularity will continue to grow. That is what I want to finish. So thank you for your attendance.